Hello again for the Future and Composite conference. So I am Hussein Nasser from KAUST University, and I will be the chair of this session. Welcome for this round table under the title of From the Smart Material Concept to Industry. So the speaker of this session are the Professor Véronique Michaud from EPFL, Switzerland, and Professor Ji Che from Georgia Tech, USA. So Professor Véronique working on fundamental of composite material processing as well as smart material and structure, including self-healing, shape and vibration control, and telluride damping. And for Professor Jerry, as you see in the previous presentation, Professor Jerry's research is in the broad field of nonlinear mechanics of active polymer. So he worked in recent years on investigating integrating active material with 3D printing. So before start, just to remember that the people on the panel list can ask questions directly and they can interact directly with the speaker. So it's a roundtable session, so they can the discussion can be directly with the speaker. And people on the attendees can write the question on Q&A. So now let's start. I keep the talk for Professor Véronique and Professor Jerry.
Yes, thank you. We have a small presentation which I will try to share and see if it works. So it was just to launch the discussion. We discussed briefly with Jerry and also with Hussein on what to say and what to do. And I think it started from the concept that smart materials, we hear a lot about these. It's not always clear what these are and how to implement them into industrial concepts and not just nice publications. So just to remind you briefly what are smart materials, I think, oops, sorry, I'm just, we all agree that, I mean, it's a very, it's a very wide definition. They're often called intelligent materials or responsive materials. And if we look at the Wikipedia, which is now what everybody looks at, especially our students, these are materials that have been designed to have one or more properties that can be significantly changed in a controlled fashion with an external stimuli, such as stress, moisture, electric, magnetic fields, light, temperature, pH, whatever. So the idea is really that it's a material that can adapt in a controlled manner and with an external stimulus. And in the composite field, because composites are heterogeneous, these are good materials to embed all kinds of active devices. And for us in the definition, it's mostly composite materials that have other functions beyond just the load bearing. And they really have the ability to respond to an external stimuli. So then the question is, what are smart composite concepts? So you've seen some this afternoon, so I think everybody agrees. There are many possibilities. They can be strain sensing, it can be structural health monitoring, it could be healing, could be moisture or temperature response, energy storage and generation, EMI shielding, vibration reduction. It could be, and they are smart thanks to interaction with many elements. So it could be either electricity or magnetic fields, but also through the environment, strain, temperature, humidity, and so on. So it's a little bit difficult to see where they stop because you can say that the material that deforms when you strain it is a smart material because it responds to strain. But typically we would agree that these have to respond to other things and they have to respond in a very controlled manner. So it's a very vibrant research topic. There are many, many articles. And coming into the discussion is the fact that we see a lot of promising results, a lot of laboratory experiments, but not so many industrial applications yet. And so the industrial applications are really most of what we can find now are elements that are externally applied under the form of patches, but they're not embedded into the composite structure. So you have a lot of fiber optic sensors, for example, that are used now in structures such as windmill blades, for example. But they are, most of the time, they are actually put as a patch or in a fiber, in a veil or something as just the last layer on top of composite. You have a lot of piezoelectric patches that have been put for health monitoring, sensing, and so on. You have also nano composite layers that, for example, can be used for conductivity, but they are used as paints or external layers. Same for solar cells. Solar cells are glued or mounted on systems, but they are not really embedded into the system. So, so there are many potential hurdles. I have a question. So before talking about the hurdles, because you will tell me what you think the hurdles are, or us, and then we can discuss if we agree. But do you have examples of industrially available smart composites that? And the question, because now, of course, with this workshop, we are also considering what's happening in Saudi Arabia. Are there such companies that are active in Saudi Arabia? We saw on the first day a lot of presentations from companies mostly active in producing composite or producing raw materials. So are there companies working in these? And then a bit provocative question is, do we need specific companies, or do we need just producers of elements like fiber optic sensors, and then they are embedded during the part production with prepregs? So in this case, it's more like a diverse application, and then the part manufacturing production should involve these companies to install these elements. So I don't know, Jerry, if you would like to add something?
Yeah, just to comment, it's open discussion. So if someone have a comment or response to this question, he can directly raise hand and answer.
I don't know if anybody has any question. Yes, Gilles.
Yeah, maybe.
Or maybe I can jump a bit in the discussion. No, I think there is a question here is that when it comes to smart material and 3D printing, there is clearly from the beginning a gap between two different communities, right? There are the people who look more on the 3D printing in the way, for example, Jerry was presenting in his presentation. So this is more oriented towards maybe soft robotics or consumer product. I mean, not necessarily structural elements. So here we are going to all this technique of 2D printing. And then there are people who come more from structural mechanics, like people who are, really using composite, like long fiber composites and everything, in which the type of 3D printing that they are using from the beginning is typically fiber placement or things like this. That is the way you are laminating a large composite structure, right? And there is a big gap between both worlds is the concept of consolidation during the printing. That means if you go to structural composites, you have a consolidation of the material, right? To make sure that you can ensure the level of mechanical properties you need for structural mechanics. So I think this is a big gap in, this is actually a question that I would like to ask to Jerry, who is really an expert in 3D printing for smart materials. In all this printing technology, there is no real concept of consolidation, but means a way to mitigate porosities or things like this. What are the direction for this to make sure that in this 3D printing that are more done for multifunctionalities or relatively low mechanical properties, what are the direction to bring this consolidation phase that exists in structural mechanics, but not so much in this classical 3D, in this over 3D printing? Is there any path for this to do this? Or?
It's a very good question. I think in my view, just 3D printing going into two directions. One, really looking at industrial applications, and they call it production level fabrications. In that case, typically it's a DLP, like a carbons working on. The other one, I think HP, more like a powder by fusion type of thing. I think they're looking at embedding the sensors into the system. I know HP is interested in those things, but for real applications, they just print just one material because I think carbon has their new shoe just come out. Adidas have the shoe come out, essentially printed by carbon 3D printer. I think price is about $230. It's not super expensive. And so that's they're looking at production level. Essentially, just you need to print about 10 million shoes in order to make it profitable. So the view is very different. The other approach is FDM. I think FDM is a lot of time just as prototyping. That it's have a slower speed, but it has a larger area printing. So there might be possibility just incorporating some kind of functions into it, because you probably recently see people can print house, and that should become popular in the US. If people start to sell 3D printed house, you can buy things, they can print it just in 1 week for you. In that area, I think you might be able to consider put some kind of sensors in the house, make a house smarter. I think that might be the area to go. Just my understanding. And then also you go to the aerospace industry. But those are primarily, it's metal additive manufacturing. In the metal additive manufacturing, you might even be harder to make multi-material. Because really that's rely on very high temperature and processing, and lots of material we deal with cannot go that high temperature. So that's my take. Just that if you to the production level, the way of their thinking is very different. Because, for example, Adidas print these shoes, and we're thinking about you can customize the shoe, right? That actually be a big advantage. But actually, I got a chance to talk to Joseph Desimon, who's actually the founder of the Carbon, and they said Adidas they don't care about the different type of shoes. Just one shoe, they just print quickly. That's all they want. They really want just like if you can print 10 million shoes, because they sell like 100 million shoes a year. Even more than 100 million, probably, 1 billion shoes. That's their more model they're looking at. So it's kind of different. Integrating the sensing, those things, you might be just probably, we had discussion yesterday, probably just smart production, high value, more important applications such as aerospace, defense applications might be possible.
But there is something that will be, because my point is about the difference of technology that you have typically in aerospace or in consumer electronics. What I mean is, and something that will be interesting online with what you presented, that is about merging different processing technologies together. We didn't see too much work so far about people trying to merge like what you do classically in aeronautics, like tape placement or thing like this, with printing technologies that you develop, for example, to make deposition of sensors in line on the placement module. You know what I mean? So trying to merge things that are more for structural mechanics together with consumer electronic system. This also, Véronique, you want to?
Yeah, I mean, what you mentioned, I don't think this is really commercially available yet, but there are a lot of people working on this, on doing a mix. Jerry presented a mix between different additive manufacturing techniques, and there are evolutions also on using regular composite processing techniques for making the bulk of the part, and then coming and 3D printing conductive pastes or whatever, some kind of a smart layer on top of it, because this is a way to gain time also and to make it a little bit easier to quickly adapt to industrial practice, because you're not completely revolutionizing and you're using also compression molding or autoclave molding. So I've seen things like that researched, but I don't know if they're really up to the stage where they are in production. But this is a bit linked to what I meant as a patch also. I know for fiber optic sensing, we've worked a lot on that. And integrating into the composite, embedding into the composite can have good points, but it's also very tricky. And there are many, many tricky points also linked to the perturbation it creates in terms of mechanical properties, but also how do you hook up your part to the, you know, to the sensing, the rest of the sensing network. We see all these pictures always, and they're always a bunch of crocodile, you know, things that are here. And when you do it for real, you need to find a good way to connect everything, all the sensors and so on. So that's why now it's done for fiber optics. It's really, a lot of it is done by gluing a final layer of composite that contains the fiber optics to protect them, but that's it. And so it's a kind of an add-on onto a normal production.
Mm. So if you go
maybe it's the way to go. I mean, at least it's the way to go fast to industry. It doesn't mean we should stop working on integration.
Since I have two experts here, I have a question that, you know, when you go to continuous fibers, so there is, you are always constrained by the topology of the fiber, right? Because it's a continuous fiber. What is the way to get rid of this? Is there, do you think there is a direction? I mean, for example, Martin showed some ideas in which he's doing some 3D optimization and in which he is reconstructing some, not really fibers, but at least domain with anisotropy and stiffer orientations within the material. I mean, is there any direction in which instead of really printing continuous fibers, we print differently or whatever, but in a way that at the end we are not constrained by this continuity of the fibers anymore, and that could bring some direction for structural mechanics? I don't see any, but that's why I asked the question. But maybe
I know Marty's design, and it's a little bit hard to realize, especially if you think about the industrial application of the composites. It's a primarily carbon fiber reinforced. Even the currently 3D printed carbon fiber, the failing rate is actually relatively low compared to the commercial ones. Mm. I think Mark Ford, that's the company making this carbon fiber filled composites. It's kind of nylon based. I think their failing rate is 30%.
There are several companies now making long fiber reinforced 3D printing, but they all have the problem of the consolidation. So either you have to accept that the part is not of very high quality in terms of the consolidation, or you need to post-process the part. So either by having rollers when you print, a bit like AFP in the end, or by having a post-processing in a press, for example, in a mold afterwards, but which is...
so at the end, it becomes very close to a classical tape placement, but with a thinner...
Yes, but you have a little bit of more flexibility in the fiber orientation, because you can really deposit the fibers as you want them. So you can really make some kind of optimization, topological optimization of the fiber placement. And then you can assemble even different parts that have different morphology. But it means that you need to have a mold, a press. So in terms of cost and everything, it's a little bit of it's less practical for sure.
But something that is interesting is that when you discuss with aerospace and aeronautic players, I mean, there seems to be more positive about 3D printing about metals, right? Because when you look at metallic part that you can achieve with 3D printing, probably it meets better the requirement that they have from the beginning, the baseline requirement. So it seems to be performing better. I mean, in terms of, so it's 3D printing, I'm sure it,
The other reason of that is that for them, it's interesting to replace, subtractive manufacturing of metals, where very often they had 95% of scrap, when they have to machine a very precise part, at least in aerospace. And composites has been an additive manufacturing technique from the beginning, because we try to minimize the waste from the beginning. So I think it's also a reason why metallic maybe has a better edge. But Vasilis, sorry, you had a question.
Yeah, maybe we have a question from Professor Vasilis.
I just want to say that additive manufacturing, I don't think that is ideal manufacturing method for mass production. It's clear for me. And also, in the case of printing, as Veronique just told, in case of printing continuous fiber composites, thermoplastic composites with additive manufacturing, then you have a lot of porosity inside, and then practically you lose the advantages that you have. So I don't think that, but in the case of metals, for replacement, for repair, and this kind of things, I think that this is a way that will work. This multi-material printing is another story. It's completely different concept, and probably but again, not for massive production. I cannot see that additive manufacturing can be used for massive production. This is my feeling.
I agree with you. Just additive manufacturing, just two aspects. It is not good for massive production, but for the AM industry, their view just if you don't have mass production, then industry would not survive. That's so it's kind of two different story. That's why I'm saying just because I sort of talked to HP quite a bit, and their view just you cannot be just make a smaller. You know, if you do not sell too much, then yeah. But you're right. Just certainly the personalized small production, you start to see more applications. You start to see more. For example, I know Delta Airlines, they're interested in 3D printing. The way they're interested is because you can imagine you have airplane flying out and to a small place, then a part just got broken, and maybe just a kind of just a cabin door got broken, and then according to regulation you cannot fly the airplane anymore, so then they have to send another airplane, or the idea if you can put a printer, you can print that parts to put it on and let it flying back to their major hub, and so that's the idea. And then they have special requirements about the filament, those things. And you do see those kind of applications start to, I think you can see more and more these kind of applications start to pop up, and then there may be opportunities.
Yeah. But when we discuss about massive production and reactivity, it was very interesting to see how 3D printing was perceived, you know, during the beginning of the COVID crisis last year. I don't know how it was in your country, but for example, when you went to Paris or to France, they were in shortage of some plastic part for some medical systems and everything. And here 3D printing became the things to do. You know, they worked hundreds of printers together in the same building to start printing parts of medical systems and everything. So I don't know if this was just a pure commercial thinking, or I don't know, because I mean, probably it was not the best way to react, but it changed a little bit the perception of people when it comes to 3D printing, like a quick reactive system, something like this. When it comes to mass production, I have a question about, Jerry, you discussed a little bit about this, about what they see in the Middle East, probably like a massive market is civil engineering, for example. This is something I don't know much, but what do you think about the future of 3D printing for civil engineering? I know for civil engineering, there are already a couple of Chinese companies who are 3D printing full houses.
Yeah.
But I don't know. What do you think? This is same thing. This is a pure commercial stuff. This is, I mean, pure.
I think in the US they do it now. They have a commercial just come out. They can print a house, but I'm not sure you can buy. You dare to buy it or not? But they can 3D print. It's very fast. They just promise they can do one house maybe in 1 week. You know, in the US typically if you build a house, typically it takes about 6 months to build a house, and they can do it in 1 week. And it's a fully customized custom designed. It's just using the printer, they print the house. I think in California, they start to sell those houses.
I don't know this much. So what is the material they are using for bigger?
I think those are more just concrete.
Concrete, yeah. I think you can 3D print concrete. Yeah.
It's 3D printing concretes. It's coming from the kind of big area printing, right? Essentially, just you got a big motion stage, like and just moving around.
So this does not help at all in solving the CO2 climate problems related to concrete, right? Because it's exactly the same. It's the same raw material. It's the same, yeah. So no, it's concrete.
Right, but I'm not sure how they reinforce that. Typically, you print the concrete structure. You have to reinforce it, right? You have a steels inside. So I don't know that how they do it.
Yeah, good point.
And they print everything.
We do have some questions in the Q&A that I cannot really see because now my desktop is all used up.
Yeah.
But if you want, we can also answer.
Yeah, I can read this question.
Have you conducted commercial study comparing the 3D printing of composite material in comparison with the current composite forming applications? I assume installation charge must be different besides the quality. Mm-hmm. That's a very good point. Essentially, yes. I mean, commercial production, I think it's faster, right? Using autoclave, those things make the composites. And but currently the 3D print is relatively small. So we have that's why we're discussing here just what will be the potential applications.
Okay, so we have another question also from Zuhair. The question is, what will be the ideal way to manufacture the FRP with long carbon fiber optimized 3D structure by topology optimization for structural load bearing application?
Good question. I think that's a bit what we were saying. If there are good ways to do 3D printing with long fiber FRP, that you can just do the topology optimization and then deposit the fibers according to what you found. So you have to kind of balance the topology optimization with the 3D printing scenario that you can do. It's a good way to do it, even if you need to post-process a bit behind to kind of do the final consolidation. It's quite expensive. So I don't know if it's the best, but for some parts, it might be interesting to do it, especially for customized parts for biomedical application and things like that.
Okay, maybe I have one question or some comment about if we return back to smart material, about the gap between the research and the industry. So we see that a huge number of research is made, especially on smart material and polymer, activate polymer. But if we look to the application or to the industry, it's very small, as Véronique mentioned before. So what do you think is the problem or the obstacle to transfer this research to industry? Maybe the reliability, maybe the cost of fabrication, maybe I don't know.
So we put some propositions here. You tell us if you agree with them. It's a long list.
Yes, Gilles, I don't know if you want.
I don't want to take all the time. Just yeah. But I don't know. My point of view is that actually there is, in terms of application, it is not so small. It depends which domain, which field you think about. If you feel about consumer electronics and things like this, or let's say, sport, leisure, things like this, there are plenty of application on the market already of 3D printing. It's because we come with a background more of structural mechanics. So in structural mechanics, there is less application. But if you go to in general, the application, they are not so small. So I have a question.
Yeah. So, sorry, I just have one, because for us, smart composites are not only 3D printed composites. It's any composite that has sensing, data, healing, actuation. So most of them are actually not done by 3D printing, but done by traditional techniques like liquid composite molding or press forming or whatever. So that's why, 3D printing is one way which could be a good driver for these. So I think you're jumping to the conclusions already. But there are many other smart composite concepts, like for example, health monitoring with fiber optic sensors in windmill blades. It's not done by additive manufacturing. It's done by just traditional, techniques. But then still, they are smart composites if you want, because they are able to monitor strains or some liners that can monitor strain also for pressure vessels and stuff like that. These are also smart composites.
I agree. Yeah. I agree. No, Vasilis, I think Vasilis has a point here.
Also, smart composites also multifunctionality is an idea for composites. I mean, to also introduce through the thickness electrical conductivity or through the thickness thermal conductivity, which is something that in several applications, for example, in the case of space thermal applications, thermal conductivity is very, very, very much demanding, very requested for avoiding cooling system for the electronics. So all these are capabilities that can pass to the market. I mean, currently we have modified prepregs with nanotubes or with some graphene layers that provide this kind of properties through the thickness, electrical conductivity and thermal conductivity too. So this multifunctionality is also an idea.
Yeah, I think, as you said, if you think about the limitations, I will say probably one of the main limitations is that when people are looking at the improvement, they are looking mainly at one of the physics. And when you create a multifunctional material, people, they want to add functionality, but they don't want to lose on the initial function, right?
Yes.
And there are plenty of cases, for example, when you start to introduce nanoparticle in a composite, where you actually, if you don't do it correctly, you might kill the properties of the composite, right? So that's why you can see plenty of studies that show very big improvement on one or two physics, but maybe the third physics that is also important for the application is going to be completely compromised. So when you go to real applications, it's actually you need to be able to make a compromise between everything, and this is maybe something that is not mature enough and that is slowing down a little bit the real applications. So, I don't know. Yeah.
Yeah, what we discussed yesterday also is indeed, but it's a bit linked into that it's difficult to get funding to do the work that is needed to go beyond just a small concept that you do in the lab with where you focus on one property, you demonstrate something, you get a publication, the PhD student is happy and everybody's happy. But then how to implement this into industry, they come back to you and they say, well, okay, you increased this and that, but you lost on many other, or actually you don't know if you lost because you never measured. And what is the durability? What is the fatigue lifetime of your beautiful material? What is whatever the impact resistance and so on. And there, it's very difficult because often it's more tedious engineering work than just scientific research. So it's difficult to get it funded. And also it's very difficult because if you want to model the impact resistance of a multi-material something, then it becomes very, very tricky as well. So I think we're not, often the research, the knowledge that we have is not mature enough. So these are difficult points indeed to be able to propose these into an industrial practice, especially
so that means,
aerospace.
Yeah. So that means what you say is that classical research team cannot really be convincing to make the case for multifunctional materials. You need to have teams now. I mean, because multifunctionality means multifunctional characterization, coupled physics, plenty of things. But now just a guy who is coming from mechanics or chemical engineering or material science cannot do alone, right? So maybe
you need multidisciplinary teams, and you need some kind of bridging funds or bridging studies to be able to go to the whole process of finding, or optimizing the material so that it doesn't lose too much on other properties.
There is a place in Toulouse that's largely funded by Airbus that tries to do that. It's one of their technical research institutes. Gilles, I don't know if you remember, it's the Saint-Exupéry Technical Research Institute.
Mm.
They really try and do that. So they embed Airbus engineers with academic researchers for a limited amount of time. And the goal is to try and transition the work from the academic work to, in that particular case, Airbus, but they have other.
You mean it's Saint-Exupéry? Is the IRT, c'est ça?
IRT, yes.
Yeah, okay, yeah. Yeah. That was created in France. Indeed, there are several of these. It's a bit like the Fraunhofer Institute in Germany. So these are kind of a bit of a transitioning institutes to go and bridge indeed between the research and the practice.
Yeah. The one I know best is the one in Toulouse.
Yeah, Saint-Exupéry. Mm-hmm.
It's really about the TR level, right?
Yes, exactly.
Lots of work we're doing really just at very fundamental, maybe just TR1, TR3.
Mm-hmm.
If you do the transfer, it has to go up to TR5 or 6, even 7. That's probably can do the transfer. For us, it's the biggest issue, just from the general idea demonstration to make it real work. There's lots of engineering, have to do. And essentially just it's very hard to do engineering thing in academia setting because the PhD student want to publish paper and we get funding. If you do engineering, you're dealing with small details and the student cannot graduate, then you have lots of those challenges.
Actually, in what you presented, the students was really good because they already put a lot of engineering in what you are doing, so to be able to do what you do.
Those are you cannot publish, right?
Yeah, but then you can see what you can do now. So what you can publish now.
But you can do more after that. But when we first published the paper, the reviewer asked us, "What is the scientific challenge?"
Mm-hmm.
And my students said, "Just putting together is very hard." I said, "I thought that's not a scientific challenge, right?" But it does take time.
Yeah.
The next students who is getting everything right.
Right. Just like we did computational mechanics, right? You spend 2 years to make computer code. You just cannot publish until that is done. You generate some new results, show the advantage. But the programming the code, you just cannot publish because those are considered also as engineering. So same thing here. Just lots of challenges. Just you put things together. You need to make a software, make interface, but nobody, if you in the scientific community, they just don't value that too much.
So I think what you say here is a very, very important point. I mean, when you are going to multidisciplinarity and multiphysics, you are going to feel where you need a lot of time before you can start to understand what you do and to control what you are doing. And I think this is a little bit not aligned with the current way of thinking in the academic community where you need to publish all the time. Sometimes you need a lot of time if you want to do something that is good and consistent. And as you said, you might need a couple of years before you can write something that you're happy with, right?
Yes.
So
it's kind of a culture, right? I think in lots of places, I don't know what's the KIC's culture. The funding agencies sometimes ask, what is can you connect it to industry directly? And what's the really, direct application? What's the economic impact you can generate? In the US, typically they do not ask that much of questions. They always ask a future impact. And in that case, that sometimes just becomes, not a real thing that's memorable, those things. That's my view. But it's a hard question for us to answer. I think that's
it's and it really depends also on the needs from industry. Indeed, there's really a gap.
I have one or two projects with industry. They want us to develop some material. They have tons of requirements.
Yeah.
Essentially, we spend lots of times, and you cannot publish those work. The student got bored. Student got worried. They want to print something for high temperature, high moisture. It is a very challenging problem. very good adhesion, you know, high temperature, perform like 1 week, 2 weeks. It's pretty challenging. And
so yeah. Anyway, I can just
yeah, we have
the next slide since we have
just
now
5 minutes.
We found some.
So
I looked yesterday.
if you have,
so
yeah,
of course, this one you will hear about tomorrow. The compare because this one that comes from our lab, and this is an adventure. But there are some available smart composites, but very few, and a lot of kind of new companies. So I mean, for example, with Vitrimers, which is a new type of polymers now, there are some thermosets with these new resins or this reinforced that use some specific elements, ductile elements to steel wires basically into composites. So there are some, but it's a bit tricky to find. And indeed, the questions are really what are the needs, what are the driving forces, and we mentioned this, the early adopters, and you mentioned it for the 3D printing. It's really often those companies that like sports, for example, or consumer goods that don't have all the certifications that you would have in other, like in aerospace or in biomedical fields. So
if you go to oil and gas, for example, oil and gas, so there are more and more smart composites, especially when it comes to pipes. So now you can find off the market pipes in which you embed optical fibers on the circumference during the fabrication of the pipe. So you have typically eight fibers that are during the extrusion of the pipe like this. So so this is used typically, you know, if you want to locate a little bit some ground motion of the ground or some leaks in your pipes and everything. So this is something that exists on the market today.
Okay.
Seems to work pretty well, at least in thermoplastic pipes. There are a lot of need in the oil and gas, for example, when it comes about monitoring drilling conditions. So this is something when you go to high temperature, high pressure in the upstream environment. Here that would be good to have smart material who are able to monitor a little bit the well condition during the drilling. That's the main needs, or how to make. When you come to composite, for example, I was discussing about these glass fibers, but this is not the solution to everything. A typical problem in pipe industries is when you have a pipe, but when you have a pipeline with hundreds and hundreds of kilometers, how can you locate a leak, right? Or how can you locate a problem in the wall of the pipe or something like this? So when you have a metallic pipe, it's easy to do because you have an electromagnetic coupling with the metal. So you can put in the pipe what you call a pig, that is a gauge that you put inside the flow and that is going to travel with the flow. But you cannot do it with composite pipe. So this is a big question. Imagine you have 500 kilometers of pipe and you have a leak somewhere. How do you locate the leak? So these are still open questions today. So optical fibers are partially a response, but you know, optical fibers, when you put them on the ground, if you have impact and everything, they don't like it too much. So it's not really a large scale engineering solution for the case. So these are open questions in the oil and gas.
Is not possible with optic fiber?
It is possible, but it's not. I mean, to locate a leak, not that much. You're going to locate perturbation, but then how are you going to interpret this perturbation? That can be due to many things, you know. So,
Dr. Kumar.
Yeah.
Okay.
Yeah, Professor Lubino, if you allow me, I would like to add a couple of points there. So we had a major project funded by Abu Dhabi National Oil Company, essentially to replace existing metallic structures by polymer and polymer-based composites, particularly enabled by 3D printing. So we kind of explored a couple of polymers in that context, particularly polyethylene and sorry. I'm sorry about that. So we explored polyethylene and polypropylene, particularly incorporating carbon nanotubes to enable self-sensing. And just to exactly address your question, so there are some portable printers which can be used to straight away put some kind of smart patch on these pipes to really monitor the structural health of these pipes. And I don't know whether really it's practiced even in aerospace industry, but then to repair some kind of corrosion related cracks or surface cracks on the aircraft fuselage, they use some kind of portable 3D printers to patch these cracks.
Yeah, no, you can put patches in that, but what I mean is this is a very local information. If you have hundreds of kilometers of pipe, you know, it becomes difficult to monitor a cloud of sensors. There is another systematic problems also if you go to oil and gas is that they don't like at all anything that has to do with electricity.
So no wiring or
or nothing that is going to be too much. So that's why they like optical fibers.
Yes.
Okay, so it's the time to finish this discussion. So if someone have the last word to say it before close this interesting discussion.
Yeah, this is our last slide. What we hear. There are some developments that are going in the right direction. So I think what we did not mention also is there are lots of development in energy storage and harvesting that can be adapted to composite structures that are quite interesting to look at. And then the additive manufacturing techniques we discussed a lot, they can be a way to integrate these sensors or patches or whatever in a better way.
Yeah, so a need for much more multi-physics, much more multidisciplinarity to make demonstrations that can be convincing to the industry. I think this is what I heard from most of you. Right? Yeah.
Yeah.
Growing needs, development. Yeah, just the last question. I don't know if I have time, Véronique. We have time for 5 minutes more.
Well,
yeah.
I'm fine. Huh?
Just a general thought about 3D printing and everything. Don't you think that we are at the middle of what it should be used for? What I mean is, if you look at industry today, you have massive industries that are using mass production techniques to produce thousands and thousands and thousands of parts by injections and everything and so on. So they do massive production, right? And on the other side, 3D printing today is very popular for the guy in his living room who is downloading a file and is using his 3D printer and everything, right? So you have a little bit the two extreme, right? Personal and don't you think that in the future 3D printing might be a way to delocalize a little bit more the production? That means you are going to see plenty of local factories capable of manufacturing many things because it's very versatile. It's very flexible. You can make many different things. And then, I don't know, maybe it's a future. I mean, maybe the industry is going to change, you know, instead of having massive production things, so we'll have small structures that are going to maybe to be a little bit more in low production, but much more local. And then people are going to, you know, Amazon is going directly to fabricate these things locally and ship it to you. I don't know, maybe in 20 years, it will completely change the way we are using the 3D printing.
I think it's, as we mentioned, for some things, mostly spare parts, repair, customized things, it will be the way to go because already it's been used and it's growing. And now for big things, I don't know if it makes sense, but why not? I mean, but I think for it will not be the full, I mean, not everything will move into 3D printing for sure, but for some markets, that will be the way to go, clearly. Also for in the biomedical field, it's been growing a lot because you can make prosthetic, devices or in tooth, in dentistry and everything. Now everybody's doing things.
Right now, the biggest market for the 3D printing is actually dentistry.
Yeah.
The molds, the brace, these are now just they make lots of 3D printed. The market is very big. Everybody's doing that right now. But in the future, like exactly as you said, people like more as a customized design than even not 3D print another application, just print the molds. right? You can print the molds, maybe make 100 parts, and then you can have some design. Then you can make another printed molds. That's another application area for 3D printing. But as you more customized designs, and then you start to see more applications. So this is still kind of, I think it's growing. Yeah.
Yeah, for sure.
But it's going to take some time. That's just the, yeah. And also in the future, you consider, for example, you know, sustainability, all those things. 3D printing give you more advantage compared to the conventional subtractive manufacturing.
Yeah.
And then, yeah. And then about the more general question that you have, Véronique, about smart materials and what limit their usage and all. I mean, I think that when you are an industrial company today, it's very complicated to control the full chain of skills that you need to do these kind of things, because you need to control the sensors, the location of the sensors, the post-treatment, the AI, everything, the way you are going to integrate it in your company. And I think, I mean, there is a small thinking to have about the education of the students in this, because today you are not designing a structural health monitoring system by designing a sensor, right? You design a cloud of sensors with an observation strategy. I mean, it's very complex in terms of skills.
Yeah,
it's much more different compared to the time where we were designing a strain gauge and we put the strain gauge and we get a strain, right? It's so yeah. I mean, in terms of education, there is a big questions to have.
Yeah. Yeah, that is true. And,
okay, so any other comment or question?
I just wanted to reinforce that from the viewpoint of research and education, and especially research outside materials and 3D printing. 3D printers are just like magic. It really allows us to bring the real world much closer to the students, and I believe it's really excellent for the students. Jill, you were talking about, you know, will we see like micro manufacturing throughout the world? And I would say that during the onset of COVID, when the world froze, local printers were like so useful. Even in my university, the university printers were not available, but the student still had a 3D printer in his home, and he was able to keep on doing his research. Of course, you know, it was not what was built was not like very solid or whatever. But hey, you know, he did not stop. He was able to keep going. So this is really a beautiful beautiful thing to have.
I think during the COVID, the 3D printer company, especially those desktop printer companies, they're actually grows very significantly.
Yes. Yeah.
Just because people work at home, they can buy a printer to do things at home.
No, and I agree also, these 3D printing devices, I mean, if you go to many labs that are not at all doing manufacturing of materials and know nothing about polymers, they all have a 3D printer somewhere in the corner because they are making stuff for their experiment. In physics, there are lots of people who are doing whatever, you know, some quantum something, whatever, and they have a 3D printer because they make little gizmos that are, you know, useful to hold the camera, to position something, or so it's really it's interesting because then they come to us sometimes with the weirdest questions, and we're like, what's you know, why do you want to know about the melting point of polyamide? You know, it's like, well, so it's,
every institution probably have a few thousand 3D printers.
Yeah, maybe. Everybody, they're just like breeding like rabbits. It's amazing. So but I think it's great. It's really empowering a lot of people to do stuff now. So.
Yeah, exactly. It's empowering people. It's interesting during the COVID crisis to see how this everybody thought that they can do something because by using 3D printing, right? You saw plenty of initiatives here and here and here, and it would not have happened. I mean, it was really I can do something, not waiting for manufacturing. So it was.
Yeah, and it's a very interesting community with a lot of open source, softwares and designs that people can share. So it's also empowering a lot of people all over the world to do stuff.
Okay, so if nobody have any question, so we can finish now this interesting discussion. And of course, you can contact maybe Véronique or Jerry if you have something to discuss. So thank you for your happy birthday to Véronique. So we have on that comment.
All the best.
Okay.
All the best, Véronique.
Thank you, Paul. See you tomorrow.
Okay.
See you tomorrow.
At 2 p.m. for the session of recyclable composites, right? That is going to start with Véronique.
Yeah. Okay.
Yeah.
See you tomorrow at 2 p.m.
Okay.
Thank you, Jerry. Thank you, Véronique.
Bye.
Thank you, Mercedes, John, Eric.
Bye-bye.
Bye-bye.
Thank you, Gilles.
And too bad we're not all meeting together. That would be so much more fun than being by Zoom.
Soon, don't worry. Everything is
let's hope. Let's hope.
In a couple of years, that will be fixed. It's okay.
Okay. Bye-bye. Ciao.